Okay, so here's a lecture on polymers. Should be lecture 7, and it will be a review on polymers. Should just be a review of materials, which most of us have already taken. So there are two different kinds of polymers. The first being natural, and of course they're synthetic, but we'll get to that in a moment. So naturally occurring polymers are things that are derived from living organisms, so things that come from nature. And some examples of that would be silk, wool, wood, DNA, cellulose, and proteins. All of those things which you can find in most organisms. And so the other type of polymer is a synthetic polymer. So things that are made by humans, they're not naturally occurring in nature. And those polymers are usually petroleum based. So not only is petroleum used for energy purposes, but it's also used as the base for many polymers, many plastics, rubbers, and fibers are derived from other things. But for most plastics and rubbers, they are petroleum based with some new bioplastics being developed. But like I said, a majority of them are still petroleum based. And those, of course, are derived from petroleum being mostly carbon and hydrogen. And so some characteristics of polymers. So first, let's note that poly means multiple or many, and mer means unit or part. So a polymer is multiple units or multiple parts or many units, many parts. So a monomer is a molecule of low molecular weight that may be bonded to other molecules to form a polymer. So a polymer can be many monomers combined together that formed that polymer. So a polymer is a macromolecule of high molecular weight made up of repeating small molecules linked together, usually by covalent bonds. And keep in mind that covalent bonds are some of the strongest bonds. So your polymers tend to be stronger or have higher mechanical property values than monomers. And here are some examples of monomer structures and, of course, polymer structures. And so now we'll take a look at some of those molecular structures, or actually the 4 molecular structures that occur within polymers. So linear, as you see pictured here, it's made of repeat units that are joined together end to end, forming a single chain. They're long, flexible chains. They usually form van der Waal and hydrogen bonding between the chains, meaning that they're not very strong. Van der Waals is your weakest form of bonding, and hydrogen is just slightly above that. So their bonds are not very strong. And some examples of that would be nylon, polymethyl mecrolate, or commercially known as acrylic, polyethylene, plastic, simple plastic, polyvinyl chloride, which is PVC, and that's what most plumbing systems now use for their piping. And there is also branched molecular structures. So branches result from side reactions that occur during the synthesis of a polymer. So as you can see here, there is a side reaction going on that connects a little branch between these two pieces. So these are two linear structures that are being connected by this branch. So they usually have a lower chain packing efficiency due to side branches. And if you remember, chain packing efficiency is how many chains you can fit within a certain unit. So its efficiency isn't very high. It can't fit a lot of chains within a unit. And it tends to have a lower polymer density, and it's usually more of a translucent plastic An example of this would be HDPE, which is used pretty often as a insulator for PVC pipes or other kinds of pipes in plumbing systems. And here are our last two molecular structures. So cross-linked molecular structures have adjacent chains that are joined together by covalent bonds. So here you can see one of those adjacent chains, and then another one, and then another one. They usually achieve this during synthesis or by a non-reversible chemical reaction. Another thing to note is that polymers, because polymers are very reactive, especially those that are derived from petroleum, so synthetic polymers. And so an example of that would be vulcanized synthetic rubber, which is what makes up your tires, and that is a petroleum-based product. And so another molecular structure is network. And so this is a multifunctional monomer forming 3 or more active covalent bonds. So covalent bonds is your strongest form of bonding, so it's a pretty strong form of bonding. And so you have molecular bonds, or network bonds, and covalent bonds all throughout here, making up this network. It's kind of got like a honeycomb look going on. And some examples of that would be epoxies, polyurethanes, soles of shoes, and those things tend to be stronger. So some characteristics of polymers. So thermoplastics versus thermosettings. These are two different ways that polymers can also be characterized. And so they're classified in this manner according to their temperature. So T sub M is their melting transition temperature, and that occurs in crystalline polymers. And if you remember, crystalline simply means that it has a structure within it. And so at this point, the temperature, the melting temperature occurs, and they fall out of their structures. So it no longer has a crystalline structure, and it's melting. So now the volume is increased, and oftentimes it can turn into a liquid. Usually this is your more recyclable stuff. And another property to keep in mind is your glass transition temperature, and this occurs in amorphous polymers. So polymers that don't have a crystalline structure. That's what amorphous means. Or amorphous also means like glass. So at this temperature, the polymers become hard and brittle like glass. And so here in this plot to the right, you can see how the melting temperature and the glass temperature kind of sit within different kinds of polymers. So here you have a mobile liquid, a viscous liquid, a rubber, tough plastic, partially crystalline plastic, and crystalline solid. And thermal properties. So thermoplastics, they can dissolve, melt, and become malleable when they're heated or put under some temperature. And when they take a certain shape, they keep it once cooled. So if you put them in a mold, injection molding, or those kinds of manufacturing processes, once they've cooled down, they keep that mold that they were put into. So this heating process can be repeated indefinitely. So thermoplastics tend to be pretty recyclable. There are a majority of your polymers that are recyclable. So it's irreversible when too high of a temperature is reached that makes some degradations within the material. So at that point, it would have to be downcycled, and you've messed with some of the mechanical properties, so it can't be used for the same purposes anymore. It can be amorphous or semicrystalline, so it can have a partial crystalline structure, or it can have no crystalline structure. It's mostly linear polymers, and there's some branch structures with flexible chains. And some examples of this would be Legos, milk and water bottles, plastic bins, and a lot of household plastics. And here to the right is a pretty interesting little diagram or figure. So if you pick up a plastic that's near you, they usually, like a water bottle, usually has one of these numbers within a little triangle at the bottom of it, and that tells you what kind of thermoplastic it is. That's how they classify them. And so, opposite of another way of classifying the polymers is thermosetting polymers. So these are permanently hard. They become permanently hard after their formation, and they do not soften when heated. So they're usually not recyclable. And they're infusible and insoluble due to their cross-link structure, so covalent cross-links between adjacent molecular chains. So your thermosettings tend to have higher mechanical properties than that of your thermoplastics. So during heat treatment, the covalent bonds anchor the chains together to resist the vibrational and rotational chain motion at high temperatures. And so irreversible degradation is also reached when you reach too high of a temperature. It's generally harder and stronger than thermoplastics, as I just stated, so the mechanical properties are usually higher. And they take shape in the polymerization process. And they're cross-linked and network polymers, and they're generally amorphous. And so here's a look at a stress strain plot, just to take a look at the mechanical properties of some of these plastics. So you do have plastic or polymers that tend to act like most regular stress strain curves that we see within metals. This one kind of shows one that looks like a metal. So it does undergo some plastic deformation, and it has an elastic region. Some of your more brittle polymers, they tend to just have an elastic region. So this is more so your rubbers this is more so things like epoxy that aren't able to undergo too much stress, and they don't give very much. So once they're pulled a little too hard or a little too far, they'll just break. So they're pretty brittle. And you have what is here an elastomeric curve. So this is your rubbers or materials of the same properties. So they tend to be able to stretch pretty far. As you can see, there's no plastic deformation portion of this curve. It's simply elastic. This is all recoverable if you were to release this material. So it would come back to the original state of the material. And so polymers are highly sensitive to the rate of deformation. Fracture strength of polymers in general are approximately 10% of that of metals. And deformation strength for polymers can be greater than 1,000%. Most metals deformation strain is less than 10%. So they can't be strained too much, or they'll reach their ultimate stress. But some polymers have a pretty high strain. And so some brittle material examples would be things like epoxy resins or melamine, which is used in some IKEA products usually of that quality. Epoxy resin, usually used on maybe wood tabletops. Polyester resin, some plastic materials, those that tend to have a stress strain graph that looks similar to that of a metal, something we're more used to, are PE, PP, and PA. And elastomeric materials are things like rubber and neoprene and silicone. So those are the ones that have a large recoverable strain region. So once they're let go, they're able to come back to their original length. And so another thing that polymers are highly dependent on, kind of like as we've already seen, is temperature. And so this is showing a plot of PMMA, methacrylate, and this is just an example of a polymer and how at different temperatures it can react so differently. So as you can see here at 4 degrees Celsius, it's pretty brittle. And then here, as you start to go down in temperature, it slowly starts to look a bit like a plastic stress strain curve. And then here it actually has, a max yielding stress, and then it goes into this area of plastic. So here it's a bit plastic, and then it eventually reaches its ultimate stress. And then here at 60 degrees Celsius, the very bottom plot, you can see how it also starts to reach a plastic region. But at this warmer temperature, its ultimate stress is larger than that of at 50 degrees Celsius. So polymers tend to react incredibly to their temperature. They're very temperature dependent. They're a very temperature dependent material. And so that's the conclusion of our polymer lecture. I hope this helps in finding some of your previous knowledge of polymers.